Welcome to Python for Computational Social Science and the Digital Humanities. My name's Christopher Cameron. I'm a computational scientist with the Cornell University Center for Advanced Computing. So today we're going to look at a few things. First of all, what is Python, in case you've never heard of it before? I'll talk about how Python helps support computational social science and digital humanities research, looking at a couple different aspects of the research. And then right at the end, a few resources to online resources and some on-campus resources to where you can learn some more about Python and how you can use it in your research. I want to acknowledge that it can be daunting to get started in programming if it's not something that you're already familiar with. It may look like this tangle of spaghetti on the left. There's a lot of new vocabulary, some new concepts, and when they come at you quickly, it's hard to get a clear picture of what it looks like. So this could be your first step. It's a steep learning curve at first. You can surmount it fairly quickly, maybe 10 hours of investment, but right at first you might feel like you should give up. I encourage you not to. Many people have felt the same way at the beginning. You can get through it. Even though there's a lot of concepts coming by, I want to assure you that if you're actually using Python for research, for me, this is my pie chart of how I'm spending my time. A lot of my time is spent using pandas, which is data frames. You're probably familiar with those from R or from Stata. So there's a package in Python for handling data frames. That's a lot of my work is in the pandas package. So learning how to use pandas well really pays off. You'll do some visualization. You'll probably have your favorite library. I like Plot9. And you'll use some features out of the Python standard library. But mostly you need to get good at a few things and you can do a lot of your work. There's only a small amount that involves sort of random extra packages, and they'll be specialized to the work that you're doing, so you can work towards it. So what is Python? Python is a general programming language. It contrasts with a language like R or Stata. Those are domain-specific languages, and in that case, their domain is statistics. Python has a well-defined and unified design principle, and that means that it's a simple and clean language. If you also use R, you'll notice the differences right away. R is neither of those things. Python is generally said to have be batteries included. That means it has a large standard library. Most of the common tasks that you will perform with Python will already have packages that support doing that kind of task available. So you don't have to write a lot of your own code. You can use packages that have been written and tested by other people and are trusted by the community. Another nice property of R is that it's extensible through add-ons. If you use R, you know about packages. And Stata has plugins. And Python also has packages. Has a little extra vocabulary twist. There are Python packages packages are themselves composed of modules. So you'll hear packages and modules used to refer to Python extensions. You may be wondering if you should be, you already use R, should you learn Python? I'm going to say yes. They're good for different things. They're both modern open source languages that are favored by data scientists. Python and R have a lot of overlap, but there's a few differences where I think one stands out more than the other. Python is a more general language. It does tend to be favored for deep learning, a little less so. Like R, there's a lot of people who want to use R for deep learning, and it gets better every year. R and Python are both very popular for machine learning. R does tend to be, I think, favored more for statistical analysis, at least by statisticians. But both of them have huge communities with many add-on packages, so you can use either one to do a large variety of things. The place where Python probably will help you the most is dealing with unstructured data. I found that to be challenging in R. Things like text data. There are some packages that allow it. They're relatively recent additions to the R ecosystem, but Python has had those for a long time. Another area where Python's particularly good is manipulating files on your computer. If you need to sort or reorganize or rename, Python has good utilities for doing that. It's great for data scraping, for cleaning and formatting. It's Good for has good data visualization, particularly interactive visualization. If you have existing code, it's pretty easy to interface with that. The things that I would encourage you not to, if you already know how to do an analysis well in R, you don't need to relearn that in Python. You could use Python to get your data ready for R, and then just switch back to a language that you already know. There's, I think, 3 ways that Python enhances research. One is through computational notebooks, the availability of computational notebooks and the popularization of computational notebooks for organizing your research and for communicating. Python also has a large ecosystem with many specialized packages. I'll be talking about many of those today. And this is maybe more of a way that Python enhances researchers, but it has this large community that produces documentation and tutorials. So when you need to learn something new, it's relatively easy to find information about how to do it, because many other people have probably needed to do the same task in Python, and someone has written a tutorial on it, or someone has written some good documentation, because many people are learning along with you. In your work, probably your most common use cases for Python will be collecting or gathering data, preparing data tables or other formats for statistical software, using Python itself for the data exploration, analysis, and visualization, and then later communicating and sharing your computational notebooks. There are many ways to use Python. One way is interactive use through an interpreter. That's very similar to using the R console. You type commands, and then printed results come back out of that console. You can also use Python for non-interactive scripts, something that might collect data for you each day. We'll have an example of that later. You might need to grab a website each day, check for updates. You may need to download a data file that's posted to a URL. You need to do it every day at 4 a.m. So you can write a Python script to automate that process. Another way that I've seen Python become part of a research project is that you already have an existing set of command line tools, but you need an extra process somewhere in that series of commands. So you can use Python to make a command line tool that will become part of an existing tool chain of text-based tools. I think the most common way, and the way that I'll focus on most today, is using Python in a computational notebook. In Python, that's called a Jupyter notebook, and it's transformed the way we think about keeping track of computational results. Here's an example of Python interpreter. There's not much to look at. This is using it as a calculator. You type in 2 + 2, push return, you get the answer 4 out. It's good for interactive use, but this is hard to document and share. When you want to document and share your work, computational notebooks are the way to go. The computational notebooks are sometimes called a way of performing literate analysis or recording literate analysis. It comes from the idea of literate programming, which is an old idea of combining documentation and code in a single document. It did not catch on very well in software engineering, for better or worse, but when those ideas were being debated, Mathematica implemented the idea of a mathematician's notebook all the way back in 1988. And mathematicians liked this literate notebook. They could document their code, they could document what they can perform their computations all in one place, and they like sharing it, but they didn't just like using it for literate programming. They like to go beyond documenting what their code did and use it to capture the research narrative. So they could describe what they were doing, why they were doing it, what the results meant, their interpretation. They could include references. It was a new way of writing a computational document. It was popular for scientists. So today, there's, I think, 2 major computational notebooks. One is the Jupyter Notebook for Python. Other is R Markdown, which you may have already used. There's a new version of R Markdown coming called Quarto. It's available now as a standalone thing. It's going to be incorporated into R and RStudio. But these are popular ideas, computational notebooks. And if you're not using them already, I encourage you to look into them. So when you think about the components of a research narrative, you may have things like text explanation. You might have a structure, an organizational structure imposed on these elements. You have maybe equations. You have images, code, maybe documentation about dependencies, and all of these things are components of a research narrative. In a computational notebook, you put these different components into cells, and then you arrange them into a sequence that makes a logical sequence to make sense that makes your research narrative. Usually there's some way of adding hierarchical structure or indicating hierarchical structure. And because it's a computational notebook, the code cells are executable and their outputs become subordinate cells that are part of the notebook. And so this ordering of cells is exactly what you see inside of a Jupyter notebook. There's different kinds of cells and they are ordered. There's a nice outline on the side. And that's what I mean when I talk about a computational notebook. This is one interface to a computational notebook, the Jupyterlab way of looking at it. There are other programs that use Jupyter notebooks, so you're not stuck with Jupyterlab. In Jupyterlab, you're going to view it. I'll pop it up here. This is maybe a little hard to see, but it's actually running inside of a web browser. That makes it easy to access remote servers as well. In Jupyter Notebook, it's kind of the earlier incarnation of Jupyterlab. So it's still around and you can still use it, but that transition, it's turning into Jupyterlab. Eventually Jupyter Notebook will go away. So I don't encourage you to use it, but you may hear about it. The next, you can use Jupyter Notebook inside of Visual Studio Code. It has an extension that will support writing the Jupyter Notebook format right in Visual Studio Code. You can use notebooks on Google Colab. And coming soon, you'll be able to use Jupyter Notebooks in RStudio or on RStudio Cloud. So it's a format that you can access through using many different tools you can use many different tools to create this computational notebook format called Jupyter Notebooks. Notebooks can be shared directly through GitHub or MyBinder, or you can export them to a variety of formats. With add-ons, you can even export them into websites or books. A well-written notebook will combine background information, explanation, documentation, analysis, results, discussion, and references into one document that you can share. And when someone has that document, they can reproduce your analysis and they can understand exactly what code you use to do your computations. So it's great for auditing. It's very nice for people who want to learn about your work, and it's really nice for you if you ever take a break from your work and need to come back to it after a few months to have your work well documented. So I encourage you to use notebooks in your research. The next important part of the Python package, of Python for researchers, is this ecosystem of packages. And I've put a link here to the Python package index for your future reference. And I'll name off some packages that I think are of particular relevance to the kind of work that social scientists do, and people in the digital humanities as well. So pandas is a big one. That's a data frame. If you've used R or Excel or CSV files, you're familiar with this table-like arrangement of values in rows and columns. It's kind of the classic data table. Pandas is the way to represent that kind of data in Python. And once you have a pandas data frame, it's very easy to export it to any other stats program. Or if you need to send data from another stats program into Python, that's an easy format to use as well, a CSV file. If you have network data or relational data, maybe you have communications logs or something that you need to analyze, you can use iGraph. There's several different tools. NetworkX is a very flexible tool written entirely in Python. iGraph and GraphTool are written in C and C++ respectively, so they're a little more performant. NetworkX is better for dynamic graphs though, but not to get too far in the weeds. All of these are good for representing relational data or network data. And that lets you build a network structure in memory in Python. You can query it, you can compute statistics on it, and you can use it as a data structure to navigate. You can traverse it as part of your analysis, depending on what you need to do. Once it's in this in these formats, you can export them to other tools. So if you, for instance, use Gephi for visualization, we'll have an example later on of a visualization from Gephi. Python's a good place to start to build up your data structure and then export it so that another tool can read it. Visualization tools in Python, Matplotlib is the biggest one. There's Bokeh and Plotly. They both use, they're both different from Matplotlib and they're different from each other. They're sort of three main ways to produce visualizations in Python. Plot9 is a tool that I really like. It uses Matplotlib under the hood, but it is a clone of ggplot2 if you use R and ggplot. You're already familiar with how to build plots in R. You can come over to Python and use the same strategy to build plots in Python. So it's nice for someone using both languages because it works the same on both platforms. Other important packages, I realize this is a long list and it's for your future reference. So I don't expect you to remember it all now, but I want to highlight the various packages that I think are particularly useful. There are many modules to connect to databases. Choose the right one for the particular database you need to connect to. You'll find JSON data is pretty common if you're using social media data. There's a JSON package for reading and writing JSON files. It's also common to get compressed files, particularly if you're dealing with tons of text data. That compresses very well. You may have a file that you may have a bunch of compressed files. If you decompress them, you may not have room on your computer. So it's nice for Python to be able to deal with those compressed file formats directly. So instead of decompressing every file, you can just ask Python to open the compressed files one at a time as it needs them. It saves a lot of hard disk space to be able to work with those files directly. We talked about NumPy and SciPy last week, so I won't talk about them too much today, but I have used them often for statistical distributions, for their numerical data structures like multidimensional arrays. They've got some nice image processing and other clustering and machine learning algorithms built in. I would encourage you to watch the recordings from last week's talk if you'd like to know more about those two packages. For web scraping, particularly for websites that don't offer an API or another way to query the data you want, if you have to actually gather it from the website itself, you can use Beautiful Soup 4. It's a very popular choice. If you have a difficult to scrape website, you might try Selenium. It lets you control your web browser using Python. So instead of loading the HTML directly into Python, you have Python control your browser and then capture the data that's been loaded into your browser. A few others for natural language processing, the NLTK, it's the Natural Language Toolkit. It's a popular choice. Spacy is, I think, a little more performant and more modern choice, but it incorporates language models. If you need to do something like named entity recognition because you are looking for, maybe you're looking for names in patient records, or you're looking for place names in restaurant reviews or something like that. It has tools for that kind of language of entity recognition and many other algorithms as well built in. So I'd encourage you to look at that one if you're going to be anything up to deep learning with text. Spacy is probably a good choice. Python does interface with deep learning and machine learning libraries like PyTorch and TensorFlow. It's probably one of the most popular ways to use those packages. And we're not going to talk about that today. Could be a good topic for a future talk. That it's too long of a topic to do in one talk. But these are, I think, some of the most useful Python packages, and I encourage you to, when you get this copy of the slides, to look these up and read about what they can do and think about how they could apply to your work. In general, I think it's best to get Python involved early on in your workflow, using that Python and its connected ecosystem to clean and manage your data, and then export data as needed to your specialized tools and to your stat software. That's worked well for me for my projects. So visually, you have mysterious data coming in from unknown sources. I tend to pass it through various Python packages until I get to a data frame, because a lot of my classes and my training focused on what to do when you had a data frame. So getting things into a data frame is usually a good bet. And from there, I can take it to any tool I already know how to use, or I can send it through Python and use Python to do analysis. You can also use Python to go to other formats depending on what you need. There's another, at the end of your research, there's also the sharing and communication part with Jupyter notebooks that I didn't put on this plot. So as an example of data wrangling with Python, particularly when dealing with geographic data, I'll use this particular paper as a motivation. And you could think of this as the overly political uncle problem, where they would like to examine this the common trope of political differences among extended family members leading to uncomfortable holiday gatherings. Now, they don't have individual political persuasion, but they were going to use precinct level election outcomes as a proxy for individual politics. And they want to compare the gatherings where guests were from same alignment versus opposite alignment precincts. The data they have to do this project, though, is they have precinct level election results. That's pretty standard data format. That'll be a data table. Then they have precinct shapefiles, which are not a format you probably have used before unless you've done some GIS. A shapefile is defines a polygon using the GPS coordinates, and so you can know where the boundaries of a precinct are based on the polygon that's defined for that precinct. The other part of their data was 26 billion geolocations from cell phone to tower pings. And that's something we might call a geotrace in social science. We have this, or a digital trace of a person. We can also call it that. This is the kind of thing, this is how a person's digital trace might look. This one's based on tweets, not cell phone pings, but same idea. We have these points in space for a person over time. And we see that this person spends a lot of time in Riverside. Sometimes they go to Lake Elsinore or San Diego. Sometimes they go to Las Vegas. If we zoom in, somewhere on here, there's going to be a dense collection of points for the places that they spend the most time. So if we zoomed in a lot, we would find that there's this really dense collection of points somewhere on here. I didn't actually indicate where with the arrow. Somewhere on here, there's this collection of points, and we can infer from these collections of points that maybe where a person lives or where they work or go to school. We can look at some of the other things and figure out where they shop and where they like to travel. This is the kind of data you get from cell phone towers or from geolocated Twitter data. Twitter may not be as available as it previously was for research. We're waiting for that all to shake out. But this research project, they needed to operationalize some of their variables. So people, in this case, are represented by all these device pings, these point clouds. And we have a history of where the devices were, their cell phones over time. So we have a lot of time location pairs, and we have to turn that into, we use that to represent a person moving through space and time. We need to figure out what do we mean when we say home location? Well, in this case, we're going to be looking for these clusters, tight clusters of check-ins. It's common in this kind of research to use your spatial clusters on weekday evenings at residential addresses. So it involves knowing the geocoordinates, doing some spatial clustering, and then reverse geocoding those clusters, which means the clusters have GPS coordinates, and you need to turn them into a street address so you can figure out if it's a residential or business address. Not everybody does the reverse geocoding because it's kind of computationally intense, but in any case, this is what you have to infer where someone lives based on the history of device check-ins. Another thing you would do here, once you have traces from multiple people, then you can start to identify things like people that live together or people that work together. For this paper's sake, it's where people are gathering. So you're looking for a group of people that come together at a location during a particular time interval, Thanksgiving dinner, and come from different homes. And while you're there, you might as well gather their distance traveled so you can use it as a control variable. So you know where the gathering is, you know where the person home location is, so you can compute the distance between those 2 points. So a voting precinct is a geographically defined area. To do this project, you have to figure out a person's home location, and then you have to figure out which precinct shape that home location fits into. So you have to that's another kind of GIS operation where you have to figure out what shape contains this point. That's something Python can do. And luckily, the election results are not hard because you have election results, you have precinct names, so you can actually just assign the election results to a precinct it is the same way you do in R or any kind of data table where you'd merge some data tables. So, but once we know where a person lives, we can further home location, then we can assign a precinct to them. So that part's, I think, probably the most straightforward of all of this. So in Python, to do this kind of work, you would take these geolocations. They would probably arrive in something like GeoJSON format. They might arrive in a simple text format, but either way, you're going to probably use a package like GeoPandas or Shapely to manage data that includes GPS coordinates. These are relative, a GeoPandas data table ends up being very much like a data frame, but it starts off as something more like a JSON file, which is not a tabular file structure. It's a list of keys and values. Another thing that goes into GeoPandas would be the shapefiles. You're able to, it understands and loads those. The precinct level election results you'd load into pandas, and you can use merge and combine operations on these to produce a data frame. Remember, the end goal here is that you need a data frame of gatherings where you know the alignment of the guests, and you need to know the duration of the gatherings, which you can tell from how long the points were together in space. So it takes a lot of steps and a lot of Python packages, but in the end, you can get a data frame that has what you need to fit the linear model that you probably already know how to do. It just takes a lot of steps to get to that data frame. If you're dealing with geographic data, you can use visualization in Python. Bokeh is good for this, for map overlays. I've used it in the past. In this case, a plot like this you could make with GeoPandas library and the Bokeh visualization. If you have complicated visualization, you can use a Bokeh server, which supports interactivity, like with sliders. So if you wanted to look at something happening over time, you can build yourself a little dashboard, and you'll be able to select different types of data, different people, and view it over time as you drag the slider. In this case, you're visualizing somebody's a focal node and other nodes that they've communicated with over a recent time interval, and some information about options where they can move. This is from a different project, but you can build a small dashboard to visualize your data. You can look at spatial information, temporal information, and relational information all in one dashboard using visualization through Bokeh server. So that's GIS. These are some examples of using Python for geo-related data. Another thing that Python is good for is dealing with text data. So here's an example of paper I was involved in. We were looking at letters of recommendation to see if there's any evidence of bias in the way that candidates are described. And so we had 2,000 letters, give or take. There were letters of recommendation for candidates in applying for academic positions from 2 different fields. And we wanted to replicate many earlier studies. Let me get a question in chat real quick. So it's it's important to think about the ethical side of using surveillance methods. I be more comfortable using tweet data since that's been self-published. I think the ping data is kind of creepy. It's unfortunate that it's available to companies. Companies will do this kind of research all the time. I think it's too bad for social scientists to miss out on using that same data to inform us, to inform science. But you do need to be careful, both that you are preserving the privacy of the people who are unwittingly participating in your study, and also not to make a tool that enables oppressive governments to go out and punish, to go out to use it to punish people. So it is a worthwhile consideration. I have not used cell phone data myself, but I have used Twitter location data, and that feels better because they all have the option to turn that feature on and off, and they're choosing to publish those tweets. But still worthy to think about. I'd encourage you to take the updated training on human subjects. I think Cornell's recently changed their policy on how to use this kind of data and what you need to do in order to use it and comply with the IRB regulations. So back to this text as data. So previous research had looked at word count based measures, something called linguistic. I don't think I say it here. I'll say it later. But we needed to get word counts for words in different categories. And so our data in this case is a bunch of PDFs. And what we really needed in order to do the analysis was a nice data table with counts of different categories labeled with genders of authors and candidates. And I don't have room on this slide to show how different these two things are. There's a lot of steps to go from PDFs, some of which are scanned documents, into a data table. And so the tools that I use to do this kind of work, one of them, a lot of times the letters were bundled as part of larger PDF documents that included statements of like research statements and an application and a cover letter and all this sort of thing. And then there'll be some letters of recommendation. So we had to pull those out. This PyPDF2 worked pretty well for that job. You're able to leverage enough of the extra information available in the file to identify when individual letters would start and stop. So I was able to mostly automate removing or extracting letters from application packets. And for physics, at least, I was able to identify the author and candidate name and label the output documents with those. Text extraction from PDF is not always straightforward, particularly if it's an older PDF. In this data set, a lot of the letters had been written, printed, mailed, and then scanned. So there was no text. It was a picture of a letter, not a real letter. So we needed to process all of these files using software that would do optical character recognition that turns the image of text into actual text. I didn't actually do that job with Python. I used a different scripting language that was built into the OCR software. But we did use it to help identify which files either had no text or had completely jumbled text. So you could run it through and look for the percentage of spelling errors in a file. And for a good letter from an academic, the number of spelling errors is very low. But if it has garbled OCR, then you'll find that 80% of the words are misspelled, and that's a good indication that that letter needs to be reprocessed. You also have to extract all the text and track all the document metadata, like author and candidate information. I found that I could automate this to some extent, but still wanted to hand verify the results. So we had a few undergraduate RAs to help us with that task, but most of the actual work was done by Python with a human checking it. To do the labeling, we had to detect the gender of the author. That would be a manual task because there's not a lot of clue based on. We could figure out a little bit from the name, but we didn't want to rely on just names. So this was a we did a first guess and then checked everyone to make sure that we got the right gender presentation at least assigned to each author. And for candidates, however, we could tell their gender based on their what people wrote about them. You could look at the pronouns used in the letter, and it'll be very clear that one set of gender pronouns will dominate the other in the letter, and that corresponds to the candidate's gender. Use Python for generating lists of authors and candidates, matching those values to a particular file, and then deduplicating. So Python helped with that work. That was basic file scripting. So using things like the os.path module to read file paths. Should I put their glob.glob on here? I'll make a note and put it in the slide before I send it out. We need to merge this list of names and candidates with gender data. So pandas would do that kind of job, merging two files on a keyed column that you specify. That's a regular data manipulation task. Pandas is up for it. You could have used R also. Needed to rename all the files on the disk with the right metadata, like their candidate and author and gender identifiers. Python is a great tool for going through a list of files, finding the old name, figuring out what the new name should be, and then relabeling it. And then finally, after all that relabeling and generating the lists of labels, we were able to process the text and generate the word counts. Like I said, we were following a method used by a software program called LUC. It stands for Linguistic Inquiry and Word Count. But we needed some features that weren't supported by LUC. So we used Python to perform LUC-style counts on the data. And finally, we get word count tables out of it, which we could send to our various tools. So we finally get to the data frame part. Then we could send it out to the tools. Different collaborators could do their analyses. Part of my role in this was to do a computational analysis. I was looking at open-ended analysis of the text. It was a computational approach. I used SciPy and NumPy to do a permutation-based simulation approach to figure out, both to see which words were stood out as being particularly different between genders, and also to apply a correction for false discovery rate, which is something you have to do if you're doing 30,000 comparisons. And the results I visualized with plot 9. So here's an example of some of the results. In this plot, the x-axis is associated with gender. Words that appear more frequently in letters for men are to the right, and those that are more common in letters for women are on the left. This is physics. We see that in letters for men, they were more likely to be described include words like physicist and intellectual, probably in the intellectual. These were not significant with the false discovery correction, but they would be significant if you looked for them directly. So if you weren't doing as many comparisons as we did, then these would have stood out as significant. The only one that actually passed the false discovery rate was this word brilliant, being more associated with female candidates. So for a woman who's trying to get into physics, it looks like the descriptors used to describe these candidates they emphasize commitment, maybe initiative here, and brilliance, which is kind of interesting. Looking at descriptors in social science, it's interesting to me. Again, does not survive the false correction, the false discovery rate correction, but it looks like you can make a story that maybe publications and science was maybe a little more emphasized in letters for men, research and teaching maybe a little bit more emphasized in letters for women. It's my hope that this open-ended analysis will spur future researchers to study these patterns more closely. In physics, there's not strong significant correlations of research area terms by gender. The ones that do stand out are in astrophysics, which tends to be a little more gender parity in astrophysics than high energy physics overall. but that none of these really stood out as significant. Social science research terms for social science research terms, this feels true to me, and I'd really like to see a nice follow-up study, that letters for men emphasize things like computational models. Letters for women tend to emphasize research usually with children and family. There's, I think, some evidence here, although weak because of our analysis, because it's an open-ended analysis, that women tend to study children and family more than men. Men seem to focus more on models and computation in social science. But this is an example of a kind of analysis that is enabled by Python. We have about 15 minutes left, so I'll go to another example here. This is another project looking at web scraping. So in this case, suppose you are interested in the high-end fashion resale market, and your data is 75,000 fashion items, and their listing and their sale price, and sale information in general. Like how long are they listed for? This is the example of a data source. This is First Dibs. It doesn't have an API. It is available for scraping. If you can scrape it because you don't have to log in to view it, but it's this giant marketplace. They show you 60 items at a time, and you need to get 75,000 of them, and you have to visit them each day to get their daily sale status updates and any price fluctuations. So each individual item also has a listing page, and you need to collect that at least once. You have to get the details about when it was made, where it's shipping from, who the seller is, its condition, its measurements. You want to capture all that information. And yeah, 75,000 items every day is just not a reasonable task for a human to do, no matter how many undergraduate RAs you had. There's no reasonable number of RAs to do that task. So you can use web scraping. So instead of loading these pages in a web browser, you could load them in Python. You can interact with the site programmatically. You can use Python to crawl, so it can discover the next page. You can go through one page and you can discover the next page link, and it can discover the next page link. So Python can load one page, capture the data, figure out the next URL, load it, repeat the process until it has all the data for each day. The strategy is to read the contents of the HTML documents, the web pages, with Python, and then extract the particular values that you care about. So the packages that support this kind of work, the request library can fetch the URL. It gives you the HTML that composes the website. Then you can send that HTML into Beautiful Soup, and that turns it into a nice data structure that you can query. In this case, some of the data we cared about was bundled up in a JSON formatted blob, and we needed to, after we parsed it with Beautiful Soup, we needed to take out this blob of JSON and reparse it with JSON to get at some of the values we needed. And in the end, we're stashing all of the values that we got into pandas to make a nice data frame for the day. Because this job required daily updates, the data gathering was performed as a Python script. So we'd run this script, it would run each day, collect a bunch of data, and then print out a daily updated data sheet. Ideally, we would have also put all the listing data into a database to avoid recrawling, but COVID stopped us from further development. But we did run it and get our data and parse it all in the end. And in the end, this was we didn't analyze this in Python. We made a nice set of CSV files. The person doing this research uses R. So after they got their CSV files, they would put it off in R and they could do their analysis. So this is, if you're thinking of web scraping, I'd recommend this set of packages. This is a graph from Gephi. This is just showing an example of a graph coming out of Gephi. I know you can't read any of these labels. Visualizations are nice for slideshows, but really when you're doing network research, you probably want to be able to traverse and query the graph structure. And as I mentioned before, these are the packages that let you navigate this kind of tool. There are some powerful and well-documented machine learning algorithms available in SciPy and scikit-learn. And you can visualize those outputs. In this case, I did it with Bokeh and Matplotlib. These are showing, this is one way to visualize clusters of what is it? I guess it's a bipartite graph, looking at clustering in a bipartite graph, but it's a way of visualizing the output. But these are two libraries that are particularly good for people looking at for starting machine learning. Python's also good for simulation and agent-based modeling. It's not particularly performant, but it's a good way to get started. If you're going to do simulation and agent-based models, NumPy, iGraph is one I've used. A graph tool looks like it would be a good bet, but I haven't used it yet. It's relatively new. There's also a package for modeling called SymPy that is for event-driven modeling. It's got a nice, it's well designed so that you can describe how your model should be in kind of clear language. The nice thing about SymPy is that it has been re-implemented in another faster language called Julia. So if you develop in SymPy and it's not fast enough, you can, you'd have to do some conversion, but you have a pathway to move your SymPy model into a faster language called Julia. I said I'd link to some extra information. So I have, these are some guides. These are online guides. The first one, it's a great place to start. This was written at Cornell by a person who was a postdoc. She now is a job where she's on the West Coast now. I don't remember which state though. But she wrote a book about cultural analytics in Python. It covers there's a fair amount of overlap on the things I mentioned today and the things she covers in depth in her book. This book was designed to support an InfoSci class in an introduction to coding for people from humanities and from social science. So it's really targeted at just this audience. And it's a book it's an award-winning book, and I highly encourage you to check it out. It's got 6 weeks worth or 12 weeks worth of content because it's for a whole real course here at Cornell. Automate the boring stuff with Python is a nice way to figure out places you can incorporate Python into your daily work. It's a popular place to go. It covers a lot of manipulating things on your file system and some about web scraping, but really about like using it to manipulate files and folders and organize things. Good information about that. There's 2 places I always like to point people to. Python has its own great tutorial. I particularly like the using Python as a calculator section 3 as a starting point. It's just, it gets you used to the cadence of using Python, the typing, the getting the results, and kind of understanding what it can do. It builds you, it starts simple and it builds up. So it's a good tutorial. They did a nice job designing this. It's been around a while. It's been revised and updated to match the new versions, but it has a good history behind it. Another one to get started with pandas, there's a 10 minutes to panda guide that covers the basic features. That's especially good if you've ever used a data frame or data table in any other software and you're kind of already familiar with the concept, but you just want to see how to do it in pandas. I encourage you to do the 10-minute to pandas guide. Around here on campus, resources for people learning Python. We do have our own series of talks for the Center of Advanced Computing, and a Cornell virtual workshop, which we also offer as a self-paced tutorials. We have many topics. Python is on there. R is also on there. We update those. I encourage you to check those out. Notice the CVW here instead of the www. That'll take you to the virtual workshop. The Cornell Center for Social Sciences, they are our hallmates here at CAC. They do workshops and offer computational support for social scientists. I encourage you to become an affiliate of this group, and then you'll be on their list for their workshops. They do workshops in Python and in R and other platforms. Another group that I've seen that I've been to many of the workshops. A lot of them are taught in R, but they're starting to offer Python workshops as well. This is the Cornell Statistical Consulting Unit. They are taught by statisticians. They It's a friendly group. I recommend going to as many as you can. It's a great way to get a survey of all kinds of methods. Lastly, I want to mention the Digital Collab at Olin Library. They are focused on humanities and qualitative social sciences. They offer workshops. They have office hours, open office hours, where you can say, I'm trying to do some research in, with congressional hearing records, and I want to know if I can extract information from them, and they'll pair you up with one of their consultants and give you some tips on how you could go about doing that kind of project. They also have a summer program in a graduate fellowship in digital humanities that you can apply for on this website. So these are the best resources I've seen around campus, aside from actually taking courses. If you're able to take courses in Python, look for ones offered through the InfoSci program. They have some that are focused on more focused on extracting data and then using it for something. It's Python for research and not Python for backend web development. So that could be another good resource if you're able to take the classes. I've included some appendices, which I'm not going to go through at length, just about how you can go about acquiring Jupyterlab for your own computer. This is the way I'd recommend you install it if you're just wanting to get started. Appendix 2 is many, many pages long. It is how you probably will have to eventually install and access Python. So I've put directions step by step, what you have to do to make it work. The nice thing is that using Jupyterlab Desktop, at this step where you launch a server, you'll be able to connect Jupyterlab Desktop to the server. It'll appear in a drop-down list in Jupyter Desktop. So I'm not going to go through all these slides. But I am going to include them as part of the presentation. Encourage you to have a look if you need them. But for getting started, if you don't have any particular packages you need, this Jupyterlab Desktop is a simple one download installable app that will get you up and going in Jupyterlab. I'll take any questions in chat, and thank you for participating today.